Welcome friends. Today we are going to learn the Bode plot for second order transfer function model. So the points which we are going to discuss in this lecture are: obtain the magnitude for the transfer function model of the second order system, that is omega n square divided by s square plus 2 eta omega ns plus omega n square. So we'll start with finding the magnitude and phase, then from the formulae we will find out the asymptotes. Then we will find the critical frequency, the errors at important frequencies, and thus we will plot the Bode on the semi-log paper. So this is the magnitude plot, and similarly we will determine the important values of phases at different frequencies, and accordingly we will draw the phase plot for this transfer function model. So let us start from the fundamentals. So we shall start by writing the transfer function for the second order system model, which is given as g at s equal to omega n square divided by s square plus 2 eta omega ns plus omega n square. This can be written in another form by dividing the numerator and denominator by omega n square. So if we divide the numerator and denominator by omega n square and flip the first and third terms, then we can write omega n square by omega n square is 1 plus 2 eta s by omega n plus s square by omega n square. Now if I assign s equal to j omega, so this becomes 1 divided by 1 plus 2 eta into j omega by omega n plus j square omega square by omega n square. So this derivation we have already done earlier. So we can take, because this is equal to j square equal to minus 1, so we can write it again in the form of 1 divided by, taking the real terms together, 1 minus omega square by omega n square plus j into 2 eta omega by omega n. Now what we do actually in practice, we replace omega by omega n by a convenient normalized frequency u, like this. So this can be again written in the form g at g as a function of ju can be written as equal to 1 divided by 1 minus u square plus j 2 eta u. So this makes our problem quite simpler. So again we can write it in the form of magnitude and phase. So for that we used to multiply the numerator and denominator by complex conjugate. So g of ju equal to, the complex conjugate is multiplied, so it becomes 1 minus u square minus j 2 eta u divided by 1 minus u square whole square plus 2 eta u whole square. So this is again it in the form of complex number, so we can write it in polar form. So this can be written in the form of 1 divided by square root of 1 minus u square whole square plus 2 eta u square, and again the phase is because this minus sign is there, so minus tan inverse 2 eta u divided by 1 minus u square. So this is the polar form. So this one can be further used in finding the values of the logarithmic of the gain for different frequency values which are of our interest. So first we will start with the asymptote, which will be coming from very low frequency up to the corner frequency. Then the second asymptote will go from the corner frequency to the high frequencies. So let us see how it comes. Start writing by 20 log s10 mod of g at ju equals to, here we can write, because the magnitude is radical in the denominator, so we can write minus 20 log of base 10. So because of the radical, 1 minus u square whole square plus 2 eta u whole square. This one will again have the square term, so this can go in the front like this minus, so this term is 1 by 2, so this comes in the front, so it becomes minus 10 log of base 10 mod of 1 minus u square whole square plus 2 eta u square, like this. Take the first case when the value of omega is very much less than omega n. Omega is very much less than omega n, which implies that omega by omega n is very much less than 1, which implies that u is very much less than 1. So in that case we can write 20 log base 10 mod of g at j omega. This should be equal to, so you have the minus 20 in front, so log of, you see when u is very much less than 1, then the first term in the bracket will be equal to 1 and the second term will be cancelled, or it will be negligible, so it will become log 1 actually. So log 1 or 1 by 2, this will become 0. So this is our first asymptote. This is, you can write asymptote 1, asymptote 1. Let us start with the second asymptote. So omega is very much greater than omega n, which implies that u is very much greater than 1. So in that case 20 log base 10 mod of g at j omega, g at j omega is equal to, here we see that minus 20 will be there in front, and if we have taken the square root term, so it will become minus 20 by 2 log of base 10. Here the first term, that is for the real part of the complex number, the first term will have u dominating, and this u will be to the power of 4. So because of that, this first term will dominate the second term, on only this u to the power 4 will be remaining. So u to the power 4, because this will become minus u square whole square, so this will eventually become u to the power 4. That 4 will come in front, so it will become minus 40 log of base 10 mod of u. So we can understand that the second asymptote will be, this is second asymptote number 2. This will become a linear function of log of the frequency in the normalized form. So because we have already studied that in the semi-log plot the x-axis is already plotted in logarithmic term. So if we take logarithmic of the frequency axis, then it will be linear on the x-axis. So even though the frequency increases exponentially, here we are having the linear function, because the y-axis, the magnitude will be a function of something which is linear, or it is linearized due to the engagement of log. Now we have to see that how, because we have different damping ratios, the value of eta are available, so we have to see how for different damping ratios the plot will be impacted. So let us consider the case for damping ratio eta equal to 1, where we have 20 log base 10 mod of g at j omega equals to minus 20 log base 10. So you can see, if you simplify the number, that is you are simplifying in terms of damping ratio equal to 1, so how it will impact the situation. So this is equal to mod of 1 minus omega square u square, sorry, it is u square 1 minus u square whole square plus 2 eta u square mod of this, and a square root has gone in front like this. Here I am seeing that this damping ratio becomes 1, equal to 1. So how it is changed, how it is modified, minus 10 log mod of 1 minus u square whole square plus 2 u whole square. If you simplify it, you will see that it will again acquire the square term, 1 minus u power 4 minus 2 u square plus 4 u square. This is equal to minus 10 log of base 10, 1 minus, sorry, this is 1 plus u power 4. These two are combined, so it becomes plus 2 u square, and this is nothing but this is equal to minus 10 log of base 10, 1 plus u square, this whole square. So this again becomes minus 20 log base 10, 1 plus u square, 1 plus u square. Now you see, when u is very much less than 1, in that case 20 log base 10 mod g at j omega will become 0. Very simple from the expression. You see the story when u is very much greater than 1. In that case 20 log base 10 mod g at j omega is equal to minus 20 log base 10. So the second term will dominate, it becomes mod u square. So mod u square, that is equal to minus 40 log base 10 mod u. Now you see, for damping ratio 1, the slope of the magnitude will change by 40 decibels, means it will reduce by 40 decibels if the frequency is increased by 10 times. So here if I consider the situation, when your u equals to 10 times, I have normalized because this is u equals to omega by omega n, which is equal to 10, means omega is increased to 10 times, so it is increased by 1 decade. So in that case, the gain will equal to the decibel gain will be equal to minus 40 log base 10 out of 10. This is equal to minus 40. It means when you go to 10 times higher frequency, the gain will reduce by 40 decibels. So in this way I can understand that if my first asymptote is a straight line at 0 decibel, and second asymptote is at slope, so it should vary by minus 40 decibel when I am changing the frequency from omega n to 10 omega n. So it should be made clear. Let us draw the plot and see how it comes. Let us draw the plot of it. So this is the semi-log paper on which I can draw the plot. Here you can see that one asymptote is coming from infinity up to the corner frequency. So corner frequency omega by omega n is equal to 1 at which point? Here you can see omega by omega n equals to 1. So this is becoming the corner frequency, because if we put omega equals to omega 1 or equal to 1, the second asymptote becomes 0 decibel. So that is the crossing point between asymptote 1 asymptote 2. So that is the corner frequency for this plot. So let us see from 0 decibel. These are the asymptotes only. I am drawing the asymptote. Okay, so this 0 decibel is extending infinitely, but at the corner frequency I am having the second asymptote. This is the first asymptote. The second asymptote, which will have a slope of minus 40 decibels. So this minus 40 decibels means from 0 decibel to minus 40 decibel, from 0 decibel to minus 40 decibel. This will be reached in 1 decade. So here I should have the second asymptote like this. These are the approximates. Now to find the actual plot for this, what we should do, we have to find out we have to find out 20 log base 10 mod of g at j omega for u equals to u for u equal to 2, right? So for this, how it will come? It should come as minus 20 log of base 10. So if the square root term is taken ahead, it's minus 20 by 10 log of base 10, 1 minus, here u square, instead of u square it will become 2 square, 1 minus 2 square, plus 2 into 1 into 2 whole square. So if you simplify it, minus 10 log base 10, 1 minus 4 plus 4, 1 minus 4 plus 4, so it becomes plus 4. So this value you will get for the frequency which is double the corner frequency. Similarly, you can find out the situation when 20 log base 10 g at j omega u equals to 1 by 2. So again you can find out equals to minus 20 by 2 log of base 10, 1 minus 1 by 2 square, 1 minus 1 by 2 square. This is, sorry, here this should be y square in front, 1 minus u square whole square, and this should be 1 minus 2 square whole square. This should also be whole square. So you have to solve it. And similarly here 1 minus square whole square plus 2 into 1 into 1 by 2 square whole square. So if you solve it, you will get the value of the correction which is required to draw the final plots. So in this way we can draw it for u equals to 10 and further values. So exact plot can be drawn with these corrections. So now I am drawing the final plot. So this should look like this. It should come along with the asymptotes, but gradually it should turn like this, like this. So this is your asymptote 2 and this is the final plot. This is the final plot. Actual magnitude plot. So we can understand that if you are having the value of damping ratio 1, then this is similar to the type 0 first order transfer function, just the power has been doubled, so slope has also been doubled, which is negative. But now if you keep on increasing the value of damping ratio, you will see that the second term becomes bigger. So the effect of that will come as this one. This will gradually come like this. So it will, corner frequency will be attained like this. It will, maybe this is 0.3 or something. So if we can understand that the this corner frequency will see the peak because of the reduction of the damping ratio. So in case you draw the plot using computer, so you can see how it looks like. You see how the plot looks like. This is how the Bode magnitude of a second order system looks like. Now is the time we should go for the phase plot. So you have to understand that if you are plotting this quantity, you are plotting this quantity in a polar phase or complex plane. So this is imaginary part of g at j omega, and this is real part of g at j omega. Now you can see that when the value of the frequency is very less, the real part is dominant and this is 1. But when it increases gradually at omega equals to omega n crosses the imaginary axis, because at that time real part will be 0, then the plot should be like this. So that from that knowledge we can find out the phase plot in such a way that phase angle comma phi equal to minus tan inverse of 2 eta u divided by 1 minus u square. So when u is very much less than 1, what we'll get? Phi equals to 0. Simple. This point we'll get the first point, this one. Now consider the higher frequency. When u is very much greater than 1, u is very much greater than 1. So how we get the phase? You see here, what should be the phase? Phase should be minus 180 degree, right? So when you are finding the phase for a Bode, for a transfer function in Bode, you have to keep in mind of the plot with respect to omega in imaginary plane, on the imaginary plane, because here we see that omega is very much less than omega n, and I say that far away omega is very much greater than omega n. So if this concept is in mind, then you can keep the value of the angle along with the sign very confidently. Now for u equals to 1, we find that the corner frequency phi equals to minus 90 degree. You can draw it, you can find it confidently using the formula also. U equals to 1, this is infinity, so this is minus 90 degree. So how we can plot for it? Let us see. So if we want to plot for it, you have to start at 0. So we start at 0. The situation will be like this. Start at 0, you are crossing the minus 90 degree, this line minus 90 degree at the corner frequency, so we start at 0 and we will go like this. So you can see the x-axis is the normalized frequency. We can take it as unity, because this is the ratio of the frequency, and y-axis is linear itself, which is the phase, and here it has been taken in degrees. So how that for different damping ratios, how it comes, let us see. Let us see how it comes for the different damping ratios. You can see that for damping ratio 1, this is the case for damping ratio 1. So this is as same as you are drawing for a system with of type 0 first order with the order of the system squared. Then if you increase the damping, if you decrease the damping ratio, gradually the system becomes stiff like this. So you see that there is abrupt change in the phase angle. So this is how for a second order system transfer function model you can draw the polar plot. Both its phase and magnitude can be drawn, and we have to consider the different values of the damping ratio. So this much is for today. One illustration I would like to share with you, where you see that if the damping ratio changes, so how the response can be experienced in time plot. So here you can see the first figure. This is the figure 1. First figure is showing the Bode magnitude, second one is showing the Bode phase, and third one is the response in time. So here third one, you can see the magnitude, how it changes. As the damping ratio decreases, there are going to be more oscillations. You can see if there is less damping, there will be more oscillations. So we can correlate the frequency domain response with time domain response in such a way. When the damping ratio is changing, there will be change in the time domain response also. So this correlation we shall learn little later in more detail. But this much is for today, and for the next session we will go for the examples of Bode plot for a simple integrator, differentiator, and the combination of different transfer functions. So this is the textbook. I generally refer this book. Other books are by Shom series, and this is by Professor Syed Hassan Said. This is also a good book. And if you want to ask queries after this session, you can write me email through controlsystemsfaq@gmail.com. And if you like this lecture, then you can press the like button and subscribe the channel to stay connected. You can set the bell button for notifications. Thank you for your patient listening.